For decades, banana cultivation followed a familiar pattern. Farmers planted banana trees, harvested the fruit, and then moved on, leaving behind massive piles of thick banana stems. These stems, technically known as pseudostems, are not true wood but dense layers of fibrous plant tissue filled with water and natural compounds. After fruiting, each banana plant dies, and the stem is cut down to make room for the next growth cycle. Traditionally, these stems were considered useless waste. They were left in fields to rot, burned, or at best chopped and mixed back into the soil as low-grade organic matter. On a global scale, this meant millions of tons of biomass were discarded every year without much thought. The idea that banana stems could hold serious economic value was once almost unthinkable. They were heavy, bulky, difficult to transport, and full of moisture, making them costly to handle. Compared to timber, cotton, or synthetic fibers, banana stems seemed impractical. Yet hidden inside these wet, layered structures was something extraordinary: long, strong natural fibers with properties comparable to some of the most widely used materials in the world. For generations, small communities in parts of Asia used banana fibers by hand to make ropes, mats, and simple textiles. However, these practices were slow, labor-intensive, and limited to local use. Scaling them up to an industrial level seemed impossible. What changed everything was a combination of necessity and innovation. As environmental concerns grew, industries began searching for alternatives to synthetic materials derived from fossil fuels. Plastic pollution, textile waste, and the carbon footprint of traditional manufacturing pushed engineers and researchers to look again at natural fibers. At the same time, banana farming continued to expand globally, especially in tropical regions. This created a paradox: while the world needed sustainable raw materials, it was also producing enormous amounts of agricultural waste. The banana stem sat right at the center of this problem, waiting to be reimagined. The transformation begins in the fields themselves. Instead of viewing banana stems as trash, modern supply chains now treat them as a secondary crop. Once the bananas are harvested, the stems are carefully cut and collected with the same level of planning as the fruit. Timing matters. Fresh stems contain fibers that are stronger and easier to extract. Farmers coordinate with processing facilities so the stems can be transported quickly, reducing decay and preserving quality. What was once a cleanup task becomes an income-generating activity, adding value at the very first stage of production. When these stems arrive at a high-tech processing facility, their journey as waste officially ends. They enter a system designed to extract maximum value from every layer of plant material. Through mechanical separation, water-assisted processing, and precision engineering, the dense pulp is stripped away to reveal long, continuous fibers. These fibers are surprisingly versatile. They are naturally strong, lightweight, breathable, and biodegradable. With proper treatment, they can rival conventional fibers used in textiles, packaging, and industrial composites. This shift fundamentally changes the economics of banana farming. Farmers are no longer dependent solely on the price of fruit, which can fluctuate due to weather, disease, and global market forces. Banana stems create a parallel revenue stream. Instead of paying for disposal or spending labor hours clearing waste, farmers can sell stems to processing plants. In regions where agriculture provides livelihoods for millions, this added income can be transformative. It encourages better land management, reduces field waste, and strengthens rural economies. From an industrial perspective, banana stem fiber represents a breakthrough in sustainable sourcing. Unlike cotton, which requires vast amounts of water and pesticides, banana plants already exist for food production. No additional land is needed, and no extra crops are planted solely for fiber. The raw material is a byproduct, meaning its environmental cost is already absorbed by food agriculture. This dramatically improves the sustainability profile of any product made from banana fibers. As industries begin to adopt banana stem fiber, its applications continue to expand. In textiles, it can be spun into yarn and woven into fabrics that are breathable, durable, and naturally textured. These fabrics appeal to eco-conscious consumers looking for alternatives to synthetic or resource-intensive materials. In packaging, banana fibers can be molded into biodegradable trays, boxes, and cushioning materials, replacing plastic and styrofoam. In construction and automotive industries, the fibers can be combined with resins to create lightweight composite panels that reduce overall material weight and carbon emissions. What makes this transformation especially powerful is the concept of total utilization. The banana stem is not valuable only for its fibers. The liquid sap extracted during processing contains natural compounds with antibacterial and antioxidant properties. This sap can be refined and used in cosmetics, dyes, and even traditional medicines. Meanwhile, the leftover pulp and biomass can be converted into organic fertilizer, compost, or biodegradable products. In some advanced facilities, this biomass is also used to generate energy, powering parts of the factory itself. The result is a near-zero waste system where every component of the stem has a purpose. This approach represents a fundamental shift in how industries view waste. Instead of asking how to dispose of agricultural byproducts, manufacturers ask how to design systems that turn them into resources. Banana stems are a perfect example because their availability is predictable and renewable. Banana plants grow quickly, harvest cycles are frequent, and production is widespread across many countries. This consistency makes banana stems a reliable raw material for large-scale operations. On a global level, the implications are significant. Countries that produce large quantities of bananas often struggle with agricultural waste management and limited industrial diversification. By investing in banana stem processing, these regions can build new industries around existing crops. This creates jobs not only in factories but also in logistics, engineering, quality control, and research. It encourages skill development and technological transfer, helping agricultural economies move up the value chain. Environmentally, the benefits compound over time. Reduced field waste means fewer emissions from decomposition and burning. Replacing synthetic materials with banana fiber-based alternatives lowers reliance on fossil fuels. Products made from natural fibers are easier to recycle or compost at the end of their life cycle. Together, these changes contribute to a more circular economy, where materials flow continuously rather than ending up in landfills or oceans. Perhaps the most important aspect of this transformation is how quietly it happens. There is no dramatic visual difference between a banana plantation yesterday and today. The fruit still looks the same, and the plants grow as they always have. The revolution takes place behind the scenes, inside factories and supply chains, where perception changes. What was once ignored is now measured, optimized, and valued. Banana stems stop being a problem to solve and become an opportunity to scale. This shift also challenges long-held assumptions about what counts as a premium material. Traditionally, value was associated with rarity or complexity. Banana stems are neither rare nor exotic. They are abundant, ordinary, and familiar. Yet through technology and thoughtful design, they become high-performance materials capable of competing in demanding markets. This redefinition of value is at the heart of sustainable innovation. As consumer awareness grows, products made from banana stem fibers carry a powerful story. They represent waste turned into worth, nature working alongside technology, and agriculture feeding not only people but entire industries. For brands and manufacturers, this story matters. It connects environmental responsibility with tangible action, not just marketing promises. In the end, the transformation of banana stem waste into a high-value resource is more than a technical achievement. It is a mindset shift. It proves that sustainability does not always require inventing something new from scratch. Sometimes, it simply requires looking differently at what we already have. The banana stem, once cut and forgotten, now stands as a symbol of how innovation can unlock hidden potential in the most overlooked places. The transformation of banana stems from agricultural waste into a consistent, high-value industrial resource would not be possible without one critical factor: high-tech automation. At the scale required to supply global markets, manual labor and traditional methods simply cannot deliver the precision, speed, or reliability needed. Automation is the invisible engine that powers the entire process, turning an unpredictable natural material into a standardized product that meets strict international requirements. In the largest banana stem factories, technology does not merely assist human workers, it defines the rhythm, accuracy, and intelligence of the operation. The journey of automation begins the moment banana stems enter the factory. Unlike uniform synthetic materials, banana stems vary widely in size, thickness, moisture content, and fiber density. This natural variability presents a serious challenge. In older processing systems, such differences led to inconsistent quality and high waste rates. Modern factories solve this problem using advanced sensor arrays. As each stem moves along the conveyor belt, laser scanners, optical cameras, and moisture sensors analyze it in real time. These systems measure dimensions, detect foreign objects, and assess internal moisture levels within milliseconds. The data is instantly fed into a central control system that decides how the stem should be handled at every subsequent stage. This data-driven approach replaces guesswork with precision. Automated sorting systems redirect stems based on quality, and condition. Thicker stems may be sent to extraction lines optimized for heavy material, while lighter stems follow a different path. Any material that fails to meet baseline standards is automatically removed, protecting downstream machinery and ensuring consistent output. What once required experienced human judgment is now performed faster and more accurately by machines that never tire. Cutting and sizing are another area where automation proves essential. Banana stems are dense, wet, and fibrous, making them difficult to process uniformly. High-speed cutting machines equipped with adaptive blades adjust pressure and angle in real time, responding to sensor feedback. This ensures clean cuts without crushing or damaging the internal fibers. Precise sizing is critical because uniform sections move more efficiently through extraction machines, reducing jams, wear, and energy consumption. Every cut is optimized not just for speed, but for fiber quality downstream. At the core of the factory lies the fiber extraction system, where automation reaches its most sophisticated form. Decortication machines operate in continuous loops, crushing, scraping, and separating fibers from pulp with extraordinary consistency. These machines are governed by programmable logic controllers that fine-tune pressure, speed, and water flow based on incoming data. If moisture levels rise, water pressure is adjusted. If fiber tension changes, mechanical force is recalibrated. This constant self-correction is what allows the factory to extract long, undamaged fibers at industrial scale. Water management within the extraction process is also heavily automated. Sensors monitor water quality, temperature, and flow rate to ensure fibers are washed clean without being weakened. Used water is filtered and recycled through closed-loop systems, reducing consumption and maintaining stable processing conditions. Automation here serves both quality control and sustainability goals, proving that efficiency and environmental responsibility can work together. Once fibers are extracted, automation continues to shape their journey. Drying is a deceptively complex stage. If fibers dry too quickly, they become brittle. If they dry too slowly, they risk mold or discoloration. Climate-controlled drying chambers rely on automated systems that regulate temperature, humidity, and airflow with extreme precision. Sensors placed throughout the chamber provide continuous feedback, allowing micro adjustments that maintain ideal conditions. Human operators oversee the process, but the system itself makes thousands of decisions per hour to ensure consistency. After drying, automated carding and alignment machines prepare the fibers for final use. These machines comb, straighten, and clean the fibers, removing residual impurities and aligning strands into uniform structures. Advanced vision systems inspect fiber alignment and density in real time. If irregularities appear, the machine automatically adjusts tension or speed. This level of control is essential for applications like textiles, where uniformity directly affects spinning and weaving performance. Quality control is where automation truly sets modern factories apart. Traditional inspection methods rely heavily on sampling and visual checks, which can miss subtle defects. In contrast, high-tech banana stem factories use machine vision and artificial intelligence to inspect nearly every centimeter of fiber. High-resolution cameras capture detailed images, while AI algorithms analyze texture, color, thickness, and structural integrity. These systems can detect flaws invisible to the human eye, such as micro fractures or inconsistent fiber density. What makes this system powerful is its integration with upstream processes. Quality control data does not exist in isolation. If defects exceed a certain threshold, the system traces the issue back through the production line. It might adjust cutting parameters, extraction pressure, or drying conditions automatically. This closed-loop feedback system ensures continuous improvement without interrupting production. The factory learns from itself, refining performance over time. Automation also plays a crucial role in handling byproducts. The sap and pulp extracted during processing are routed through automated pipelines into separate processing units. Filtration systems purify liquids to specific standards, monitored by sensors that track clarity, composition, and flow. Solid biomass is measured, compressed, and redirected toward fertilizer production, biodegradable materials, or energy generation. Automation ensures that byproducts are not treated as waste but as parallel resources, each with its own optimized processing path. Packaging and logistics further highlight the importance of automation. Finished fibers are weighed, bundled, and labeled by robotic systems that ensure accuracy and traceability. Each package carries digital information about its origin, processing parameters, and quality metrics. This level of traceability is increasingly demanded by global buyers who require transparency and compliance with environmental and labor standards. Automated systems make this possible at scale, eliminating human error and speeding up distribution. Beyond the factory floor, automation extends into energy management. Smart systems monitor electricity usage, water consumption, and emissions in real time. Energy-intensive processes are scheduled to align with renewable power availability, such as solar generation during daylight hours. Waste biomass can be automatically diverted to energy units that generate heat or electricity for internal use. These systems reduce operating costs while lowering environmental impact, reinforcing the factory's sustainable identity. Perhaps the most profound impact of automation is its ability to turn a complex natural material into a predictable industrial input. Manufacturers depend on consistency. Whether fibers are destined for textiles, packaging, or composites, they must behave the same way every time. Automation bridges the gap between nature's variability and industry's demand for uniformity. It transforms banana stem fiber from an experimental novelty into a dependability that engineers and designers can trust. This does not mean humans are removed from the process. On the contrary, automation changes the nature of human work. Skilled technicians, engineers, and data analysts replace manual laborers. Their role is to oversee systems, interpret data, and continuously optimize performance. This shift improves safety, reduces physical strain, and creates higher-skilled jobs within agricultural regions. In a broader sense, the use of automation in banana stem factories reflects a new industrial philosophy. Instead of forcing natural materials to conform through excessive chemical treatment or wasteful processing, technology adapts to the material itself. Machines listen, measure, and respond to what the plant offers. This respectful, data-driven approach represents the future of sustainable manufacturing. Ultimately, high-tech automation is what makes the entire banana stem industry viable at global scale. Without it, production would be slow, inconsistent, and economically fragile. With it, agricultural waste becomes a reliable resource, quality becomes measurable and repeatable, and sustainability becomes operational rather than theoretical. Automation does not just increase efficiency, it unlocks the full potential of banana stems, proving that advanced technology and natural materials can evolve together into a smarter, cleaner industrial system. The idea of a zero-waste, eco-friendly industrial system is often talked about as a future goal, but in high-tech banana stem factories, it is already a working reality. What makes this model so powerful is that sustainability is not treated as an add-on or a marketing label. Instead, it is built directly into the design of the process. Every stage is planned with one central question in mind: how can every part of the banana stem be used so that nothing is thrown away? In traditional agriculture, waste is unavoidable. After harvesting bananas, massive amounts of organic matter remain in the fields. When left to decompose or burned, this waste releases greenhouse gases and can attract pests and disease. High-tech processing facilities flip this problem into an opportunity by collecting banana stems and directing them into controlled industrial systems. The moment a stem enters the factory, it is no longer waste, it is raw material with multiple potential outcomes. The most visible product is banana fiber, but it represents only one part of the stem's value. During fiber extraction, large quantities of liquid sap are released. Instead of being drained away, this sap is captured and filtered. It contains natural compounds with antibacterial, antioxidant, and binding properties. With further refinement, it can be used in cosmetics, natural dyes, biodegradable coatings, and even traditional medicine products. What would normally be an industrial effluent becomes a valuable input for other industries. The solid pulp left behind after fiber removal is another critical element of the zero-waste model. This biomass is rich in organic matter and nutrients. In many facilities, it is dried, compressed, and converted into organic fertilizer that is returned to agricultural fields. This closes a natural loop, feeding nutrients back into the soil where new banana plants will grow. Some factories take this a step further by processing the pulp into biodegradable plates, food containers, paper products, or packaging materials, replacing plastic and single-use items. Energy use is another area where zero-waste principles come into play. Banana stem residues can be processed into bioenergy through controlled digestion or combustion systems. This energy is then used to power parts of the factory, reducing reliance on external fossil fuel sources. Combined with solar panels and energy-efficient machinery, this approach significantly lowers the overall carbon footprint of the operation. Waste is not just reduced, it actively contributes to production. Water management is handled with the same mindset. Fiber extraction requires large volumes of water, But high-tech factories rely on closed-loop systems. Water is filtered, treated, and reused multiple times before being released. Automated monitoring ensures that water quality remains stable, protecting both the fibers and the environment. By minimizing discharge and recycling water internally, these factories dramatically reduce their impact on local water resources. The zero-waste model also extends beyond the factory walls. By reducing agricultural residue in fields, farmers face fewer issues with pests, fungal growth, and uncontrolled decomposition. This improves overall farm hygiene and can reduce the need for chemical treatments. At the same time, the additional income from selling banana stems encourages better crop management and long-term sustainability. From a product lifecycle perspective, banana stem-based materials offer clear environmental advantages. Products made from natural fibers and biodegradable components break down more easily at the end of their life. Unlike plastics and synthetic composites, they do not persist in the environment for centuries. This reduces landfill pressure and lowers the risk of pollution in oceans and soil. Sustainability is not limited to the factory. It continues through the entire life of the product. Economically, the zero-waste approach strengthens resilience. Instead of relying on a single product, factories generate multiple revenue streams from fibers, sap, biomass products, fertilizer, and energy. This diversification reduces risk and makes the industry more stable in changing market conditions. Environmental responsibility and economic strength reinforce each other rather than competing. At a deeper level, this model represents a shift in industrial thinking. Waste is no longer something to manage after production. It is something to design out from the beginning. The banana stem factory becomes an ecosystem rather than a linear production line. Materials flow in cycles, outputs feed new processes, and efficiency improves naturally over time. In the broader context of global sustainability challenges, this approach offers a blueprint for other industries. It shows how agricultural byproducts can be transformed into valuable resources without additional land use or environmental strain. The success of banana stem factories proves that zero-waste manufacturing is not an idealistic concept. It is a practical, scalable solution already shaping the future of eco-friendly industry.